Hello and welcome again to Engineering Physics, and for today's video, we would now be discussing about energy. So when we say energy, it is basically the ability to do work. So, as basic as that. So dyan po nagtatapos ang ating video lecture, pero syempre joke lang. So in this case, guys, so it is said here that it is now to be the ability to do work. So from the previous discussion that we had, when we say work, it has been defined that work is to be the product of force times the displacement, assuming that force is to be constant and d is of course the displacement. So suppose that this is now to be our sample particle, and if we would be applying a certain force F onto it, so let's say that this is now to be a force F, the tendency is for this particle to go right. So it would now be this. And as you can see, since it has been moving, it would also have its own displacement already. So in that case, this is now to be its displacement. So it is measured from the initial position up until the final position. So this is now to be displacement D. And once again, assuming that this force is constant throughout the motion, work is basically equal to force times displacement. So this is to be a review from the previous video lecture that we had. So going back to the term energy, so once again, it is now to be the ability to do work. So in this sense, it is now, energy is now the particle's ability to displace by this much once that force F is to be applied. And for comparison, when we say energy, since it is now to be the ability to do work, for the car's energy, it is basically the gasoline. So the gas, the diesel, or whatsoever. Because if there is no gas in your car, the car does not have any capability to exert force F for it to displace. So once again, in this particular case, air energy is to be in terms of gas. So if you can remember from the previous video lecture once again, so work is to be in terms of Newton meter. So this is now to be in SI unit. And Newton meter is to be 1 joule. So work is to be in terms of joules. And in this case, since I have said that energy is now to be compared with gas, even though that gas is to be measured in terms of liters, or let's say ml, energy in terms of physics is to be in terms of joules also. So energy and work do have the same unit. Okay, so proceeding here, so once again, in basic physics, we would be having two general categories of energy. And the first one is what we would be calling potential energy. And the second one is what we would be calling kinetic energy. So for potential energy, it is defined here as the stored energy. So as per its word, or as per its name, so when we say potential, it means that it is basically work waiting to happen. So in Tagalog, hindi pa siya nangyayari, mangyayari pa lang. Okay, so we have two basic types of potential energy. The first one is to be the potential energy by gravity. So gravitational potential energy and elastic potential energy. So elastic potential energy. Okay, so when we say gravitational potential energy, it is basically the energy stored by virtue of gravity. So if I would just be erasing this for me to better explain gravitational potential energy, so for pretend that this is to be the ground, and let's say that there is to be an object at a certain height. So let's say that this is now to be that particular object at, let's say, a certain height h. And of course, since this object is to be a matter, it would be having its own mass. Okay, so if for example that this particular object here falls to the ground, it did work. So work is once again basically equal to force times the displacement. And if this is now to be h, height h, the displacement is to be h. And as for the force, and since it fell under the influence of gravity, so gravity, and when we say that it is now to be under influence of gravity, the force there is now to be the weight. So weight. So weight is basically mass times gravity, which you should already know. And in that case, so once again, the force exerted here was to be the force exerted by the weight, and the displacement is to be h. So with that, work is now to be equal to mass times gravity. So this is now to be the force applied times the displacement, and in this case, that is now to be h. So that is to be the work done if, of course, this particular particle falls to the ground. But what about for the potential energy? So when we say potential, once again, it is just work waiting to happen. So it did not happen yet. It is still waiting to happen. So with that, we are to assume that the particle did not really fall. But as you can see, it has the potential to fall. And it has the potential for it to have a work of mgh. So with that, since I told you earlier that it did not happen yet, so it does not have any work yet, this is basically your potential energy. So this is basically your potential energy. So potential energy is now to be equal to mg times h. And in some other books, instead of using PE, they are using U as a symbol. So U is equal to mgh, where U is to be equal to potential energy. So let us just use U for our symbol. Okay, so direct substitution, U, or the potential energy due to gravity. So gravity. So I will just be writing U grav here just for us to have this. Okay, so gravitational potential energy is equal to mgh. Okay, so that is for the first one. And as for the second one, so for the second one, this is now to be our elastic potential energy. And so what is this, by the way? So if I am to add a new slide here, and let's say that this is now to be a spring. So if this is now to be a spring, so if it is to be at rest, so if you would now be compressing it, of course, the tendency of this particular spring here is, of course, to exert a force onto your hand kasi nga naiipit mo siya. And if you are to be stretching it in this manner, the tendency of this spring is to go back to its initial position. So if you are to be exerting a force here, forces here, the tendency of this spring is to pull your hands together. So with that, if you would now, if let's say that you would now be having a certain spring here. So let's say that this is now to be the spring, which is to be in static condition. And let's say that this is now to be your object. If you would now be stretching this object, let's say that this is now to be a wall, for example. If you would now be stretching this particular object, so it's now, its new shape now is to be a little bit stretched. This is now to be your object. So I'm sorry for the presentation. So the tendency of this spring is to pull this particular object to this direction for it to return to its original position. So that is if you would be stretching the spring. But what if, for example, that instead of pulling it, so once again, instead of pulling our spring here, you have decided to compress it. So in that case, the spring would now look like this. So it would be compressed. And let's say that this is now to be your object. So the tendency of this spring is to push this particular object up until this portion. So up until this portion for it to go back to its original position. So that is for elastic potential energy. And our formula for elastic potential energy, so let us say that this is now to be PE spring. So this is now to be the potential energy for spring, and this is basically equal to 1/2 K times x squared. Whereas K is now to be equal to the force constant of the spring, so this is now to be given. And x is now to be the displacement. So in this case, if this is now to be the initial position and you have compressed it to this part, so this is now to be the value for your displacement. So there. Okay, so proceeding. So let us now proceed to kinetic energy. So as per defined here, when we say kinetic energy, it is to be the energy of a particle has by reason of its motion. So in other words, kinetic energy is to be the energy as brought about by motion or by moving. So let's have this for example for you to understand it better. So once again, we would be having our car, and let's say that there is a certain object at this particular location. So let's say that there is to be a particular object. And let's say that this car is moving at a constant speed, or may it not be constant as long as it is moving with a speed. So let's say that it is now to be moving at this direction. So if this car is once again moving, so if it is moving to the right, and if it would be hitting this particular object here, so the tendency of this object is of course to move towards the right also. So that's if the car has hit that particular object. So what really happened there is that the energy of the car was transferred onto this object, and once that this object was, the energy from this car has been transferred to this object would now have the tendency to move to the right, and it would now be subject to work since there is now to be a force present and there is now to be a displacement present. Okay, so in this case, guys, since it is now to be moving, kinetic energy or Ke is basically equal to 1/2 mass times velocity squared. So as you can see, it is very similar to the equation for elastic potential energy. It's just that in this equation, instead of us using K and instead of us using the displacement X, we would now be using mass and velocity. So there. Okay, so let us just have an example for you to understand potential energy and kinetic energy better. So in this example, it is said here that a 1.5 kilogram book is held 60 centimeters above a desk whose top is 70 centimeters above the floor. So we would be finding the potential energy of the book with respect to the desk and with respect to the floor. So before solving anything, the first thing that we will be doing is that we will be drawing the figure here for us to better visualize the problem. So it is said here that there is now to be the presence of a 1.5 kilogram book. So let's say that this is now to be the book. So if that is now to be the book, it is said that it has a mass of 1.5 kilograms. So it is held 60 centimeters above a desk. So let's pretend that this is now to be the desk. So once again, for pretension, this is now to be the desk. Okay, and it is said in the problem that this particular distance is to be said as 60 centimeters. So 60 cm. Okay, and it is also said here that the desk is to be 70 centimeters above the floor. So with that, if this is now to be the floor, so this is now to be 70 centimeters. Okay, so now that we have already known all of the parameters that we would be needing, so the next thing that we will be doing is, of course, we would now be solving for it. So for A, so what is now to be the energy with respect to the desk? So for potential energy, we will now be making use of U gravity. So U gravity, gravitational potential energy, this is now to be equal to, so if we would be getting the potential gravity with respect to the desk, so once again, this is basically mgh, where m is to be the mass, g is to be the gravitational acceleration, and h is, of course, the elevation or the height. And in this case, the height between the table and the book is said to be 60 centimeters. So with that, so mass is now to be equal to 1.5 kilograms times gravitational acceleration of 9.81 meters per second squared times height. And since we want our unit to be in terms of Newton meter for it to be converted to joules directly, what I will be doing first is that I will be converting this into its meter equivalent. So with that, multiplying my conversion factor here. So for every 1 meter, so once again, I will be converting it to meter for me to arrive at an answer of Newton meter later on. So 1 meter, for every 1 meter, there is actually 100 centimeter. So with that, centimeter would now cancel out and would leave us with an unit of meter. So with such, using the calculator to your left, this is basically equal to, so 60 divided by 100. So this is to be 0.6 meters. So I would just be converting this also. So times 1 meter divided by 100 centimeter. So centimeter would now cancel out and we would now be having an answer of 0.7 meters. Okay, so for the potential energy for gravity, so I would just be erasing this for me to have space. But take note that this is to be 0.7 meters. Okay, so moving forward, so for the potential energy here, this is now to be equal to, so 1.5 kilograms times 9.81 times what is now to be the height, so that is to be 0.6 meters. Okay, so substituting known values, so 1.5 times 9.81 times 0.6, so that is now to be equal to 8.829. So 8.829 Newton meter or joules. So joules. So this is now to be my final answer for A. And for B, so what would be the potential gravity with respect to the floor? So U gravity is equal to, so same old, mgh. And in this case, so mass did not change. So 1.5 kilograms still. Gravity is to be 9.81 meters per second squared. And h is now to be equal to not just 0.7, guys. So for the height h, that should be measured from the book up until the flooring, because as you can see here, with respect to floor. So with that, you must once again measure from the book up until the flooring. And in that case, that is to be 0.6 meters plus 0.7 meters. So I would just be writing them here. So 0.6 plus 0.7. So they are to be in terms of meters. And with such, our answer here is now to be equal to, so 1.5 times 9.81 times 0.6 plus 0.7. So our answer here is now to be equal to 19.1295 Newton meter, and this is now to be in terms of joules also. So the potential energy in terms of gravity is now to be 8.829 joules and 19.1295 joules respectively. So there. Okay, so next let us have an example of kinetic energy. So in this example, a 1.5 kilogram book is sliding along a rough horizontal surface at point A moving at 3.21 meters per second and at point B moving at 1.25 meters per second. So with that, if this is now to be the horizontal surface, and let's say that this is now to be the book. So of course, it is to be in contact with ground. I have just placed a little bit of space there for me to select the object. So okay. So it is said here that if this is now to be point A, it is now to be moving at a velocity of 3.21 meters per second. So that is at this point. And as you can see, it is now to be moving at this position. And let's pretend that this is now to be point B. It is said here that at point B, it is now to be moving at 1.25 meters per second. Okay, so for letter A, it is said here that, well, we would now be getting the work done on the book between A and B. So before proceeding with this example, for work energy theorem, it is stating here that the work done by the sum of all forces acting on a particle equals the change in the kinetic energy of the particle. So with that, the work done is basically equal to the change in kinetic energy. So when we say change in kinetic energy, this is basically equal to kinetic energy final minus kinetic energy initial. And this is also equal to, so substituting the equation here, this is to be 1 half mvf squared minus 1 half mvi squared. So this is to be the equation that we will be using for this particular problem. So for work, so that is basically the change in kinetic energy. And this is now to be equal to, so what is now to be the final velocity? So by the way, this is to be equal to 1 half mvf squared minus 1 half mvi squared. So substituting known values, so this is now to be equal to 1 half times mass. So for the mass of the book, this is now to be 1.5 kilograms. So times 1.5 kg times velocity, and our velocity final here, that is to be 1.25. So 1.25 squared. So that is for the first kinetic energy. I mean for the final kinetic energy. And for the initial kinetic energy, so minus 1 half times 1.5 times 3.21 meters per second squared. So guys, take note that you can only make use of this equation. So once again, kinetic energy is to be equal to 1 half mass times velocity squared, assuming that mass should be in terms of kilograms and velocity should be in terms of meters per second. If let's say that your mass is to be in terms of grams, you must convert it first to kilograms. And let's say that your velocity is to be in terms of centimeters per hour, you must convert it first to meters per second. Okay, so proceeding, since we already have a consistency in units here, so substituting known values and using our calculator to your left, so 1 half times 1.5 times 1.25 squared minus 1 half times 1.5 times 3.21 squared. So in here, a work of negative 6.5562 joules was done. So as you can see, from its initial velocity, 3.21, it now became 1.25. So as you can see, it slowed down. And with such, guys, we can say that the work is to be negative because the work done here is to be opposite the direction because, of course, it has slowed down. If, for example, that the particle has sped up, it means that your work is to be positive because it is along the direction of your motion. But in this case, it is not. So in Filipino, kaya negative yung work natin kasi pinabagal nga natin. No? So from 3.21, naging 1.25 siya. So that is to be, of course, in Filipino. Okay, so that is now to be our answer for letter A. So I would just be writing them here. So A, so negative 6.5562 joules. Okay, so moving forward, for letter B. So it is said here, if a work of negative 0.75 joules is done from book B to book C, how fast is it moving from point C? So let's pretend that we would be having another point here. So let's say that this is now to be point C. So velocity is now to be unknown. However, the work done in this particular portion is now to be equal to negative 0.75 joules. Okay, so with such, we can once again rewrite our equation as, so work done is to be equal to change in kinetic energy, and that is to be 1 half mvf squared minus 1 half mvi squared. So substituting known values, so we already know the value for work, which is already given in the problem, which is to be this. So with that, negative 0.75 joules. So this is to be equal to 1 half. So what is now to be the mass of the particle? So 1.5. So times 1.5 times. So what is now to be the final velocity? So that is actually the thing that we are solving for here. So that is now to be Vf. Of course, it must be squared. So minus 1 half times 1.5 times Vi squared. So what is now to be Vi? So that is now to be the initial velocity. So take note that I am using 1.25 and not 3.21 because this amount of work is only concerned from B to C and not from A to C. So if it is only covering B and C, so it means that the initial velocity here should be the velocity in B. So with that, this is now to be 1.25 meters per second squared. So now solving for the value for Vf, so I can make use of shift solve or we can just transpose it manually for you to review. Okay, so if I am to copy this to the next slide, so what I am doing is that I will be isolating Vf to one side. So what I would be doing here is that I will be transferring all of the values to the other side. So with that, negative 0.75 joules plus 1 half times 1.5 times 1.25 squared. And this is now to be equal to 1 half times 1.5 times Vf squared. So with that, cross multiplying, so instead of me using 1 half here, I would just be using 0.5. So same thing. So 1 half is basically equal to 0.5. So I would be dividing both sides by 0.5 and 1.5 for me to get rid of these values here. Or if you do not want that approach, cross multiplication, same thing. So with that, this is now to be equal to, so negative 0.75 J plus 1 half times 1.5 times 1.25 squared divided by 0.5 times 1.25. This is now to be equal to Vf squared. And since this is now to be squared, I would now be getting the square root of both sides. For me, just to arrive at an answer of Vf. So with that, Vf is basically equal to the square root of all of this, and using our calculator to your left, so square root of negative 0.75 plus 0.5 times 1.5 times 1.25 squared divided by 0.5 times 1.25. So our answer here would now be equal to 0.8216 meters per second. So this is now to be our Vf. And if you do not want to make use of this and you want to make use of technology to our advantage, so I would just be making use of shift solve here. So negative 0.75 is equal to 1 half times 1.5 times alpha x squared minus 1 half times 1.5 times 1.25 squared. So shift solve and we should arrive at the same answer, which is, okay, so mali. So going back here, so 0.75 joules plus 1 half 1.5 divided by 1.25 divided by 0.5 divided by, oops, sorry guys, this should be 1.5. So 1.5. So this should be 1.5. Okay, and with such, so resolving for our problem here, so square root of negative 0.75 plus 1 half times 1.5 times 1.25 squared divided by 0.5 times 1.5. Our answer here should be equal to 0.75 meters per second. So going back here, if you would now be trying to solve for it via shift solve. So once again, negative 0.75 is equal to 1 half times 1.5 times alpha x squared minus 0.5 times 1.5 times 1.25 squared. So shift solve equal sign. So our answer here would now be equal to 0.75. Okay, so that is now to be our correct answer here. So our answer here once again, 0.75 meters per second. Okay, so next up, so how fast would it be moving if at C? I mean, how fast would it be moving at C if a work of positive 0.75 joules were done on it from point B to point C? So same thing, it is just that instead of negative 0.75 joules, we would now be changing it to positive. So, positive. So, in my calculator here, so I would just be changing this to positive. So, shift solve. And my answer here would now be equal to 1.6008 meters per second. So, this is now to be our final answer. So, there.